Hi everyone, my name is Cecilia Aragon and I'll be your guest lecturer this week. We're going to be talking about basic principles of information visualization. This is, in my opinion, one of the most important, interesting, and fun components of the data science pipeline. We're going to be talking about how you take the data that you've collected and analyzed and then actually present it in a form that makes sense to the human brain. I'm a professor here at the University of Washington in the Department of Human-Centered Design and Engineering, and it'll be my pleasure to introduce you to this exciting subject. My research interests lie in the visual presentation of very large scientific and social data sets. So let's start with a few definitions. The word visualization is extremely overloaded. There are many possible meanings of the term. So what are we talking about when we say we're studying information visualization? Well, we want to consider the visual representation of information. The goals of information visualization include the effective communication of information or data. With clarity, that means that the information should be presented in a way that's easy to understand by a human. With integrity, you present all the data and nothing but the data. And you want to stimulate viewer engagement with the data. Our focus in this course will be on effectiveness. We're talking about the clear and effective presentation of data to the human mind. Data visualization usually falls into three academic categories: information visualization, scientific visualization, and visual analytics. Information visualization typically involves abstract information that may not have a position in space. For example, on the slide you can see a graph of stock prices around the year 2000. We graph the price, the dollar amount on the y-axis, and time on the x-axis. Scientific visualization usually involves displaying data that has a physical position in space. For example, here you see a methane combustion data set, where each of the data points has a 3D location. Visual analytics is a combination of highly interactive visual interfaces and sophisticated statistical learning algorithms. In this course, we're going to be talking about basic principles of information visualization. We're not going to be talking about scientific visualization specifically, nor about visual analytics, nor about the artistic field of visual design. The principles, however, of information visualization that we are discussing are applicable to all three domains. We will be discussing specifically this week how to map data variables to visual attributes. So why is visualization important? Say you have 1 million numbers. What's the best way to communicate that information to the human brain? Well, imagine a table of 1 million numbers. It seems almost too vast to comprehend, much less to find meaningful trends or information about it. But on the other hand, if you consider the number of pixels on your computer screen, it's typically around 1 million, and you have no trouble understanding it very quickly and being able to act on the information you've gleaned. So the human visual system is the highest bandwidth channel to the human brain, and it's the most efficient way to present large amounts of information so they make sense. Let's talk about a few examples. So maybe the first use of visualization historically was for eliciting knowledge from data. Let's suppose you have a table of numbers. We'll start with a relatively small table with only 50 rows, one for each state in the Union, 3 columns in each row: the name of the state, the percentage of college graduates in that state, and the per capita income. So you might have questions about this data, such as which state has the highest income? Is there a relationship between income and education? Finally, are there any outliers? Are there any trends? Well, obviously all the data is present, and you could take your time looking at this data. You could identify the highest and lowest numbers. You could answer all these questions from the data. Everything is presented here. But is this the most efficient way to understand this data? Here's another way of presenting the data in a scatter plot. We have per capita income on the x-axis and the percentage of college degrees on the y-axis. And as you can see, the question of which state has the highest income is instantly answered. We can see that Connecticut has the highest per capita income. Similarly, it's clear there's a trend, that there's a correlation between per capita income and the percentage of college degrees. And there's also a couple of interesting outliers. Nevada has a relatively high per capita income, but a very low percentage of college graduates. So all the information is presented in both of these forms, but the visual representation is much more efficient at presenting meaning to the human mind. Well, so, okay, the first question that might come up is, well, yeah, but all this information could more easily have been accomplished by analyzing the data with a statistical program. You could find the maximum, you can find the minimum, you can find the regression line. However, it turns out the human brain is one of the best pattern matching tools that we have. Actually, the human brain so far is still better at detecting patterns in data than any of our most sophisticated machine learning algorithms. So an immediate question that arises is, why not just use a statistical program and identify the minimum, the maximum, the trend lines, and go from there? Why bother with a visual representation? The answer is simply the graphs reveal data that statistics may not. So here's a famous example of Anscombe's quartet. Here you have 4 small data sets that are quite different, as you can see by looking at them, but they have identical linear models, that is, the identical means and the identical trend lines. Again, you could just present the data in tabular form, but see how much more information we can learn about these individual data sets just by looking at the data. So even though we have identical means, identical regression lines, these data sets are quite different. So statistics may not tell us everything about a particular data set. I hope I've managed to whet your appetite for this coming week's set of slides. I'm going to stop here and we'll continue on with more examples in the next lecture. In this lecture, we're going to talk about the heart of information visualization, data types and visual mappings. So the central problem in order to visualize data is quite simple. We need to map data sets to visual attributes. This is also known as data encoding. And the process can be described in a very straightforward manner. 1, you classify your data types. And 2, you determine which visual attributes represent data types most effectively. Of course, the devil is in the details. Let's start with data types. There are 3 basic data types: nominal, ordinal, and quantitative, which can be further subdivided into interval and ratio. I'm going to explain each of these on the next slide. So nominal data can be thought of as labels or names. An example is fruit. Apples, oranges, peaches, pears would be described as nominal data. Ordinal data has an order associated with it. So for example, the quality of meat might be described as grade A, grade AA, grade AAA. There is an implicit order, so you can clearly say that grade AAA is better than grade AA. Of the 2 types of quantitative data, interval data is where the location of 0 is arbitrary. So dates are an example. If you're looking at January 5, 2012, or location, for example, latitude 47, longitude 122. And these are like a geometric point. You can't compare them directly, but only differences, that is, intervals, can be compared. And then finally, you have ratio data, which is where the 0 is fixed. And you can think of this as any physical measurement, length, mass, counts and amounts. The origin is meaningful. Let's talk a little bit more about the differences between nominal, ordinal, and quantitative data. Sometimes it's not immediately clear, given an example, what data type that it falls into. So one of the best ways to actually identify data as nominal, ordinal, or quantitative is to look at what are the operations that are permitted on this data. So nominal data, there are really only 2 operations that are permitted, either equals or not equals. For example, with fruit, you can say the oranges are not equal to apples, and apples are equal to apples. There's no other comparison that can be made. You can't say that oranges are somehow better than apples. Ordinal data has additional operations besides equals and not equals. You can now say that one is greater than or less than another, or greater than or equal to, or less than or equal to. So for example, with the grades of meat, you can say that AAA is better than AA, and vice versa, greater than, less than. You can deal with that implicit ordering. Now moving to quantitative data with interval data, for example dates, now you can subtract. So you can measure distances or spans. You can say that not only is January 6, 2012 after January 5, 2012, but you can say the difference between those two dates is 1 day. And finally, coming to ratio data, where the 0 is fixed, now you can add division or ratios. You can measure ratios or proportions. So for example, if an object weighs 32 grams, you can say that it weighs twice as much as another object that weighs 16 grams. All right, so that's the theory. Now let's put it into practice with an exercise. I'm going to show you a spreadsheet, and I'd like you to think about which of the columns in the spreadsheet are nominal, ordinal, or quantitative. So here we have a set of sepal and petal lengths and widths for 3 species of iris. The first column you have an ID number, then a case number, next a species number, then a species name, the organ, petal or sepal, the width and length of that organ in millimeters. So why don't you take some time and think about which of these are nominal, ordinal, and quantitative. You can see that it's not as straightforward as it might appear in the first place. For example, we have numbers here that fall into the categories nominal, ordinal, and quantitative. So let's explain why each of these is defined the way it is. So the quantitative is probably the easiest. The orange data, the width and the length of the sepal and petal, are quantitative. You can say, for example, that for the first species, the length is 7 times the width. So you can perform ratios and proportions. So it's quantitative data. Now, the first two, the ID number and the case number, are ordinal. So why are they not quantitative? Well, because it's really not something where you can say that the distance between the ID number 3 and the ID number 2 has any meaning. But it clearly has an order. The ID numbers were assigned in some particular order. So therefore it's ordinal. And the cases were assigned in a particular order, but there's not necessarily a meaning for the differences between them. So the ID and the case numbers are ordinal. Now we have the species number, the species, and the organ, which are nominal. Well, it's probably pretty clear that the species name and the organ would be nominal because they're names. All you can do is say whether they're equal or not equal to each other. You can't say that the sepal is somehow greater than the petal. So those are pretty easy. But what about the species number? Why isn't that ordinal? And the answer to that is simply because in this case, the species number is simply a label. There is no order to it. It was assigned to the species simply as a labeling convention. All right? So hopefully that has been a useful example for you. All right, so moving on. We've now completed step 1 of the process of information visualization. So now let's describe how to do step 2, mapping data types to visual attributes. In 1967, Jacques Bertin, a French cartographer, made the first formalization of visual language and the first attempt at a theoretical foundation for information visualization. He identified 7 key visual attributes illustrated on the right-hand side of the page in 0, 1, and 2 dimensions. And these 7 key attributes are position, size, value or lightness, texture, color, orientation, and shape. So this is an important slide. You should probably write down these seven attributes or at least save the slide. So now that we have taxonomies of both data types and visual attributes, let's talk about how we map one to the other. So Bertin offered the following suggestions. He said there were levels of organization that you could consider. Position can be used for nominal, ordinal, or quantitative data, as can size. Now value, or lightness, can be used for nominal or ordinal data, and perhaps for quantitative data, although it's not quite as clear. And texture can be used for nominal data, maybe for ordinal data. You could imagine a denser texture might be seen as having some order over a less dense texture. And then finally, color, orientation, and shape can really only be used for nominal data. You can't really say that one color is greater than another, or that one orientation is less than another, or that a shape, a star, say, is more than or less than a circle. And further work that involves decades of research in psychology and psychophysics have established this hierarchy of perceptual properties. Humans can detect differences in position most accurately, then length, then angle and slope, then area, then volume, and least of all, color and density. So when you're assigning these attributes to your data, make sure to choose position for your most important quantitative data and save color and density for nominal data. A final note on color. Value can be perceived as ordered, so you can encode ordinal variables. In other words, you see this strip that goes from black to white, where value is increasing. You can see that there is an order to these colors. You can also even encode continuous values with a grayscale mapping, although not as well. But hue is normally perceived as unordered, so you always only want to encode nominal variables using color. There's no order to the colors on the bottom of the slide. So this was a very brief lecture on the central important problem of information visualization. In the next lecture, we'll look at exercises where you can actually put this theory into practice. Last time, we talked about the theory behind the central problem in information visualization, mapping data types to visual attributes. In this lecture, we're going to put that theory into practice. So for these exercises, I'm going to show you 3 visualizations, and in each of them, I'd like you to identify which types of data and mappings are represented. So here we have a stock chart from around 2000, the year of the dot-com bust. How many data types are represented on this graph? What are they? Are they nominal, ordinal, or quantitative? What are they mapped to? Which visual attributes, that is? And is that a good mapping? Why or why not? What is your opinion on the visualization? Take some time to study it and come up with the answers to these questions. Okay, here are the answers. It's actually quite simple. There are 2 dimensions of data represented on this chart. They're both quantitative and they're both mapped to position. You have the time, which is quantitative, or interval data, on the x-axis, and then price in dollars is mapped to the y-axis. All right, let's try another one. This is one of the earliest graphs made in 1786 by William Playfair, a Scottish engineer and the inventor of several common types of diagrams in use today. So on this diagram, how many data types are represented? What are they? Are they nominal, ordinal, or quantitative? Which visual attributes are they mapped to? And is this a good mapping? Why or why not? There are 4 dimensions of data represented in this graph. The year, which is quantitative, is mapped to position on the x-axis. Imports in pounds, also quantitative, mapped to position on the y-axis. Similarly, exports, which are quantitative, are mapped to position on the y-axis. And then finally, the balance of trade, which can be considered either nominal or ordinal, is mapped to color and area. Here we have the U.S. stock market, visualized with a version of Ben Shneiderman's tree map, where quantitative data is mapped to a set of space-filling rectangles. In this case, market capitalization is mapped to rectangle area. This was created by Martin Wattenberg in 1998. How many data types are represented? What are they? Are they nominal, ordinal, or quantitative? Which visual attributes are they mapped to? And is this a good mapping? Why or why not? In this visualization, we have 4 variables. The market capitalization, quantitative, is mapped to the rectangle area. The market sector, technology, energy, capital goods, transport, etc., is nominal data, and that's mapped to the rectangle position. Third, whether there is a gain or loss is represented by the color hue, red or green. So if there's a gain, it's green, and if there's a loss, it's red. This is nominal or perhaps ordinal data. Finally, the magnitude of the gain or loss, which is quantitative data, is represented by the color value. So you can see that the brighter the green, the greater the gain. Similarly, the brighter the red, the greater the loss. So this concludes our set of 3 exercises. I hope you found this illustration useful. Next time, we're going to talk about data combinations and dimensions. In the last lecture, we provided a set of 3 exercises on mapping data types to visual attributes. In this lecture, we're going to give more examples of data combinations and the mapping of data to visual attributes, and we'll talk about the effects of dimensionality on the visual display. So if you have a single variable to display, or univariate data, you have a plethora of choices for visualizations. Dot plots, line plots, bar graphs, or 2-key box plots are but a few of the examples. For bivariate quantitative data, the scatter plot is the most common choice. So here we have 2 quantitative variables, and the scatter plot describes the information quite clearly. Moving up to 3 dimensions, now it's getting a bit more challenging. So we can try a 3D scatter plot, but what are some of the problems? Let's look at the 3D scatter plot on the right with blue cubes. Where exactly are E and F in relation to each other? It's a bit of a problem trying to represent 3-dimensional information on a 2-dimensional surface. A better choice might be to use a 2-dimensional scatter plot with a 3rd dimension represented by some other attribute. Here we use area for the red circles for the 3rd quantitative dimension. Area is not perceived as accurately as position, so you want to put the most important dimensions on the x and y axes and save the least important or perhaps the most easily distinguished for the 3rd. Since we already discussed what are the issues in trying to map 3 variables to a 3rd spatial dimension, let's look at other ways to deal with mapping 3 variables to a visualization. So we know that 2 variables on the x and y axis can map to points. So we have scatter plots, maps, etc. Now the 3rd variable must use something like color, size, or shape. And as you can imagine, we have a very large design space. So finding the optimal mapping becomes more challenging as the number of dimensions increases. You can always use shape or different types of marks to represent nominal or categorical data. Now moving up to multidimensional data. How many variables can be depicted in an image? We've talked about 1, 2, and 3 dimensions. But what about more? Is there some perceptual limit? Starting in 1967, Bertin and others asked this question. And Bertin stated, with up to 3 rows, a data table can be constructed directly as a single image. However, an image has only 3 dimensions, and that barrier is impassable. We'll look into answering this question in the next lecture. Last time, we talked about data types, dimensions, and how to map data to visual attributes based on the number of data dimensions. Clearly, there's a large design space for this visual encoding. Information visualization is about choosing the most effective visual encoding for a given data set. In this lecture, we're going to describe how to do that. We saw earlier that there are different data types, and those can be mapped to a set of visual attributes, and some mappings are better than others. So now we have a challenge. How do we pick the best mapping of all possibilities? So in order to do this, we're going to follow 3 basic principles. importance ordering, expressiveness, and consistency. This was first described by Jock McKinley in 1986. So importance ordering has to do with encoding the most important information in the most perceptually accurate way. Expressiveness has to do with depicting all the data and only the data. And finally, consistency means that the properties of the image, the visual attributes, should match the properties of the data. I'll go into more detail on how to do this on the following slides. We'll start with importance ordering. We've seen this slide before. Now, as we discussed earlier, decades of research have taught us that certain visual attributes more accurately represent quantitative data to the human brain. McKinley defined expressiveness in the following manner. He said a set of facts is expressible in a visual language if the sentences, i.e. the visualizations, in the language express all the facts in the set of data and only the facts in the data. So what does this mean? Well, using color hue, we cannot express the fact that one item is greater than another. So color hue simply can't represent ordinal data, ordinal or quantitative data. So color hue simply can't represent ordinal or quantitative data. It's best used for nominal data. On the other hand, you don't want to express facts that are not in the data. So a length is interpreted as a quantitative value. In this incorrect use of a bar chart, the length of the bar says something untrue about the data. So on the x-axis, we have the national origin of these cars, and on the y-axis, the make and model. Now, the length of the bar suggests an ordering on the axis. So it implies that somehow Germany is greater than the USA. So therefore, using bars for nominal data is an incorrect choice. Number 3, we have consistency. The properties of the image, the visual attributes, should match the properties of the data. What this means is you don't want to do something like mapping one-dimensional data to two- or three-dimensional visual representations. This diagram represents why that's not a good idea. So here we have the price per barrel of oil represented as the height of a three-dimensional barrel. You can see the obvious problem here. Look at 1974. The price is $10.95. And then for 1979, the price is $13.34. Well, this is less than a 30% increase. And yet, the 1979 barrel looks significantly larger than the 1974 barrel. So clearly, this is an inconsistent representation. The three-dimensional representation is implying something false about the underlying data. Let's move to a data encoding exercise. Here we have a data set of cars. We have the model on the first column, the country of origin, the year, the number of cylinders, the horsepower, the miles per gallon, and finally the weight in pounds. I would like you to create a visualization that encodes all 7 dimensions of this data set. Make the perceptually appropriate choices and be prepared to explain. I'll describe the steps you need to do and show you Bertin's examples once more. So step 1, determine which columns represent nominal, ordinal, or quantitative data. Step 2, review Bertin's visual attributes on the next slide, and assign the most perceptually appropriate choices to each data set. Step 3, create a visualization that encodes as many of the 7 dimensions as you can. Don't worry if you can't get all of them, but do try to do so. To review, here are Bertin's visual attributes: position, size, value, texture, color, orientation, and shape. Are you done? Here's one attempt made by one of my students. So this is an attempt at encoding 7 variables from the CARS data set in a single visualization. So this student chose to put 2 of the quantitative variables, horsepower and miles per gallon, on the X and Y axes. The third ratio data, weight, he encoded with area of the marks. It's not a bad choice since you can only put two of those ratio variables on axes. He also chose to encode cylinders, which are quantitative interval data, by using the shape of the mark. And then finally, he used color hue for the region, Europe, Japan, or US, and color value or lightness for the year. Additionally, in his visualization, you could mouse over each of the marks, and the name of the model of the car would pop up. So, what do you think of this visualization? What works? What doesn't? And what could you do better? I'll leave that critique as an exercise for you. In this final lecture on effective visual encoding, we're going to start with two quick exercises on effective presentation of data, and then we're going to discuss 5 key techniques for increasing the amount of information represented by spatial position. So we've already talked about why effective visual encoding is important. Here is an example that I'd like you to consider. So look at these two representations of quantitative data. Here we have the top level one where color is used to represent it, and at the bottom a line graph. Why would the line graph be better to use than the color? By now you should know. It's faster to interpret. As you take the time to look at it, you can see that. There are more distinctions. You can clearly see the quantitative information much more easily with the line graph than with the color, and there are fewer errors of interpretation. Pretty simple. Is this an effective visual representation? Yes or no? If no, what's wrong with it? This visual representation is not expressive because it implies an incorrect ordinal relationship among the countries. All right, moving on to some new material. We already know from research data in human perception that spatial position is the most accurate representation of quantitative data. So how can we leverage this fact? In 1999, Card, McKinley, and Schneiderman proposed 5 techniques to increase the amount of information encoded by spatial position: composition, alignment, folding, recursion, and overloading. We're going to go through each of these slide by slide. Composition refers to an orthogonal placement of axes. You create a 2D metric space, and you can line the data up along the x and y axes in multiple different ways. Alignment. This refers to the repetition of an axis at a different position in the space. So here you see we have the same time axis repeated in 2 places, but 2 different graphs representing different amounts of information on the y-axis. Folding, continuation of an axis in an orthogonal dimension. Recursion, or the repeated subdivision of space. And finally, overloading, where we reuse the same space for different data. All right, this concludes our set of lectures on visual encoding. The next set of lectures will move to visual perception. In the previous lectures, we've been discussing data and visual mappings. Now we're going to talk about the other end of the pipeline, how that information is processed by the human brain. This is the first of 3 lectures on visual perception. 70% of our body's sense receptors reside in our eyes. Our very language resonates with the importance of our eyes. Metaphors to describe understanding often refer to vision. I see, insight, or illumination. Colin Ware stated in 2004, "The eye and the visual cortex of the brain form a massively parallel processor that provides the highest bandwidth channel into human cognitive centers." In these 3 lectures, we're going to describe how it's important to understand how visual perception works in order to effectively design visualizations. The first key principle to keep in mind is that the eye is not a camera. A better metaphor for vision was given by Christopher Healy in 1995. It's a dynamic and ongoing construction project. And it's important to keep this in mind as you go through the next 3 lectures, because when you design a visualization, if you think of the eye as a camera, it can lead you to some erroneous conclusions. Attention is selective. We all know that. It's filtered to a high degree. And it's really cognitive processes that transform the visual information into something that we can comprehend. The field of psychophysics is concerned with establishing quantitative relationships between physical stimulation and perceptual events. So we're going to be talking about some of the important discoveries made in this field in the next 3 lectures. Let's think a little bit about how to use perceptual properties. Information visualization should cause what is meaningful to stand out. So what do you see in this image? Can you see the 2 spots that differ from their surroundings? Why do you see them? We're going to answer that question in the next few slides and lectures. Some important differences between eyes and cameras. Cameras have very good optics. They have a single focus, they maintain a white balance and a single exposure. And they also do what's known as a full image capture. In other words, all the photons coming into the eye are captured with equal importance and at the same time. The eyes, on the other hand, have relatively poor optics. They're constantly scanning. This is known as saccades, the shifting of your eyes to various positions. They're constantly adjusting focus. They're constantly adapting, both the white balance and the exposure. What's really going on is a mental reconstruction of the image, sort of. As we'll find out, it's not even a complete image that's reconstructed. So here's one example. Visual perception really isn't just camera work. Looking at this checkerboard, it's pretty clear that square A is darker than square B, right? It turns out if you gray out the image, you see the truth. Square A and square B have identical pixel values. As a matter of fact, when I first saw this image, I didn't believe it. I actually put the image in Photoshop and used the eyedropper tool in order to find out what the RGB values were of those 2 squares. And yes, indeed, they are identical. So you're welcome to do the same. You can take a screen capture and test it out yourself. But it's pretty interesting. The human visual system is so dependent on context and upon reconstructing the image that we see these 2 squares, which are identical, as quite different. Color is relative, as are many other of our perceptions. If you look at this slide, doesn't it look like the X on the left-hand side is gray and the one on the right-hand side is yellow? But if you go look at where they connect in the center bottom of the slide, you'll see they're identical. And that's again because the eye perceives differences. It does not perceive actual pixel values. So in conclusion, I hope you've taken away from this lecture that the eye is not a camera. In the next 2 lectures, we're going to discuss more about how understanding visual perception can help us develop more effective visualizations. Welcome to our second lecture on visual perception. In this lecture, we'll be discussing a very intriguing property of the visual system, pre-attentive processing. I'd like you to look at this slide and tell me how many 5s there are in this array of numbers. Do you have the answer? All right, I'd like you to think about how long it took you to find them and what techniques you used to detect these 5s. And now I'm going to show you the same array with one small change. Now how many 5s? All 5s are red, by the way. Notice how easy it was to come to the answer? The color made the 5s pop out at you. Psychologists have given this property a name. Your immediate detection of the red 5s is called pre-attentive. It turns out that certain basic visual properties are detected immediately by the low-level visual system. It means they pop out at you rather than requiring a visual search through all the elements. In general, if the detection of a target takes less than about 200 to 250 milliseconds, it qualifies as pre-attentive. And the reason is because eye movements take at least 200 milliseconds. And yet we find that certain processing can be done very quickly, and this implies low-level processing in parallel before the eyes even have a chance to move. In general, if a decision takes a fixed amount of time, regardless of the number of distractors, it is considered to be pre-attentive. Now, only a limited set of properties can be perceived pre-attentively. That means without the need for focusing attention. And you can see why this would be important for designing visualizations. What can be perceived immediately? What properties are good discriminators? What can mislead viewers? How can you use the ability to process information pre-attentively to strengthen your visualization? Let's talk about a couple examples. So looking at these two squares, in which one is there a red circle, left or right? Pretty obvious, right? You could instantly see that the red circle is visible in that group of blue circles. It jumps out at you. It seems almost ridiculous to think that there might be a question. Detection of the red circle in a sea of blue circles is pre-attentive. Now, which square contains the red circle, left or right? The form, the curvature, is also pre-attentive. The curved circle pops out at you. However, you may have noticed that it doesn't seem quite as immediately obvious as the different color. Pre-attentive processing lies on a spectrum just like many other such visual features. Now, which square contains the red circle, left or right? So that one required serial search. So this is interesting. So even though form is pre-attentive and color is pre-attentive, the conjunction of the two is not. So the red circle in the sea of red square and blue circle distractors could not be perceived pre-attentively. This can be used in practice to save lives. Detection of a slanted line in a sea of vertical lines is pre-attentive. In this case, the slanted line in a number of cockpit dials is used to indicate systems failure. And I'm going to conclude with a list of pre-attentive visual properties for you to consider. For more detail, please see Christopher Healy's article on the web. The link is given in the lower right-hand corner. I hope that you found this lecture interesting and that you're able to use this information while you're designing your own visualizations. In our third and final lecture on visual perception, we'll be discussing how humans estimate magnitude. If you'll recall from our earlier lectures on mapping quantitative data to visual attributes, you can see how understanding common misperceptions or inaccuracies in the visual system can be very helpful when it comes to designing an effective visualization. We're fortunate in that there is a large body of psychophysics research that we can draw on. All right, so I'd like you to look at these two circles and tell me what is your impression of the difference in areas between the two circles. I want you to come up with two numbers. First, your first impression, and then what you think it is after considering it more. Write down both numbers, both your first impression and your more detailed analysis. So what did you get? The correct answer is 25. The idea of a power law for visual perception was first mentioned in the 19th century, but Stanley Stevens in the mid-1950s came up with a body of work to justify it, and he formalized the power law. His experimental results for perceptual estimation gave an exponent for length of pretty close to 1, so in other words, fairly accurate. But in area, 0.6 to 0.9, so you get some underestimation, and in volume, 0.5 to 0.8, even more underestimation. So in the previous slide, even though the area differential was 25, most people tend to say it's around 16. So how close did you come? And perhaps more importantly, How can you use this for designing visualizations that will be accurate and effective? It turns out cartographers have already known about this for quite some time. In the 1970s, Jay Flannery, a cartographer, conducted a set of experiments and produced a set of empirical guidelines for how to represent quantitative information using area. So what cartographers do when presenting quantitative data, they'll use apparent magnitude scaling. All right, let's consider a set of visual attributes and how good humans are at estimating magnitude. This data comes from, again, from many decades of research in psychophysics. It turns out that humans are most accurate at estimating differences in position if there's a common scale. If the scales are non-aligned, then they're slightly less accurate, but still fairly accurate. Then comes length, slope, and angle. And then much less accurate are area, and even less so volume. And finally, humans are most inaccurate at using color to judge magnitude. So again, we have evidence that the hue, saturation, and value are not very good choices to use when when representing quantitative data. So the conclusion to these 3 lectures on visual perception is that what is currently known about visual perception can aid the design process. Understanding the low-level mechanisms of the visual processing system and using that knowledge can result in improved displays. In this lecture, we're going to go through the step-by-step process of how to evaluate a visualization. The first step is to consider the purpose of the visualization and who the intended audience is. In other words, is it to educate, to inform, or is it for exploration? Is the audience the general public or a specialized body of scientists, for example? That's very important in deciding what the overall value is of this particular type of visualization. Don't make the mistake of judging a visualization without understanding the intended audience. Next, determine your initial reaction. Is it generally positive or negative? It's all right to have an emotional reaction to a visualization, but also try to step back and analyze it somewhat dispassionately. Examine the visualization in detail. What works well, what doesn't? And finally, answer questions such as the following. Is the design aesthetically pleasing? Is it immediately understandable? If not, is it understandable after a short period of study? Does it provide insight or understanding that was not obtainable with the original representation, text or table, etc.? This is very important. If the only difference between the visualization is that somebody added color to the design and made a pie chart out of it, that does not necessarily make it valuable. A visualization should add value over a textual representation, or it is not a good visualization. Fourth, does it provide insight or understanding better than some alternative visualization would? Or does it require excessive cognitive effort? What kind of visualization might have been better? For example, if somebody has given you a set of multiple pie charts and you have to compare pie wedges from one to the other, is that really the best way to make those comparisons? Or could a bar chart have done the job just as well? Maybe better. Does the visualization reveal trends, patterns, gaps, or outliers? Can the viewer make effective comparisons? Does the visualization successfully highlight important information while providing context for that information? Is new information gleaned from the visualization that wouldn't have come from an alternative method? And is the important information highlighted? And is the context not hidden? Number 7, does it distort the information? If it transforms it in some way, is this misleading or helpfully simplifying? Does it omit important information? Is it memorable? Does it use visual components properly? That is, does it represent the data using lines, color, position, etc., as we discussed in the earlier lectures? Does it transform nominal, interval, and quantitative information properly? And does it use labels and legends appropriately?